Imagine opening a door into a universe where billions of pages float in a vast digital cosmos, each one shouting for your attention, each one trying to tell you it matters. Now imagine being dropped into that universe in the mid-1990s, before Google existed, when the web was transforming into an uncontrollable explosion of documents, and finding anything, literally anything, felt like wandering through an infinite library with no card catalog, no map, and no lights. That chaotic universe is where our story begins, and where two graduate students at Stanford quietly built an idea so influential that it would become the gravitational force of the early web, reorganizing the entire digital world and launching one of the most powerful companies in history. This idea is PageRank, the ranking algorithm that didn't just bring order to the web, it rewired how humanity discovers knowledge itself. Today, we're going to peel back the curtain on how this algorithm actually works, why it was revolutionary, and how a deceptively simple mathematical insight changed the world. And if you love deep dive videos that take you into the origin stories of the technologies shaping your life, make sure you hit that like button, subscribe, and drop a comment so the algorithm, ironically, knows you want more videos like this. Our story begins with a fundamental question. In a world where anyone can publish anything, how do you determine what information is important? Traditional search engines of the early web didn't truly understand importance. They mostly relied on counting the number of times a keyword appeared on a page. This made search engines easy to manipulate. People stuffed pages with repeated words, hid keywords in white text on white backgrounds, and tricked early algorithms into thinking a page was relevant when it wasn't. The web was becoming a polluted ocean of spam, and search results were drowning in noise. But Larry Page and Sergey Brin approached the problem from an entirely different angle. Instead of looking inside the pages, they looked at the structure of the web itself. Every link from one page to another, they realized, isn't just a connection, it's a vote, a signal of trust, a citation. And citations, in academic literature, have long been used to measure importance. Could the same approach reorganize the entire World Wide Web? Could importance be measured by looking not at what pages say, but at how they're connected? This idea sounds simple now, but at the time, it was radical. The web is a gigantic directed graph. Pages are nodes, links are edges. Some pages link to thousands of others, some to none. Some pages receive countless links, others are isolated islands. But what Page and Brin recognized is that not all links should count equally. A link from a highly reputable source, say a major university, should arguably be worth far more than a link from an obscure or low-effort site.
So they drew inspiration from academic citation metrics and proposed a recursive definition of importance. A page is important if important pages link to it. This is not circular reasoning. It's a powerful mathematical principle that leads to a stable ranking value for every page. And that value, that measure of importance for each page, is what we now call the PageRank. Let's break down how this ranking actually works, and more importantly, let's turn the math into something intuitive and fun to understand. Picture a random surfer, someone who simply clicks around the internet at random. They land on a page. They look at its outgoing links. Then they pick one at random and click it. They continue this process forever. Click, move, traversing the web as a wandering explorer. Over time, where does this random surfer spend most of their time? On average, the pages they land on most often are the ones with the highest page rank. It's a probabilistic interpretation of importance. The more likely you are to end up on a page through random clicking, the more important that page is considered to be. But this random clicking behavior alone isn't enough. What if the surfer lands on a page with no outgoing links, what's called a dangling node? They'd get stuck forever. What if they get caught in a circular loop between a few pages with no escape? To fix this, Page and Brin added a brilliant twist. At any moment, with some probability, often represented as 0.15, the surfer stops following links and jumps to a completely random page. This is known as the damping factor. It ensures the system never traps the surfer, and it makes the algorithm converge reliably. The remaining probability, usually 0.85, is the chance they follow an actual link on the page they're on. This simple model, the 85% chance of following a link, and a 15% chance of teleporting to a random page, is the core of the PageRank formula. In mathematical terms, PageRank computes the eigenvector of a huge matrix representing the web graph, adjusted to incorporate the random teleportation probability. You don't need to understand eigenvectors to appreciate the elegance here. The algorithm repeatedly updates each page's importance score until it stabilizes. Over many iterations, scores stop changing meaningfully. At that point, the algorithm has assigned a definitive measure of importance to every page on the web. Now, here's where the story gets interesting. This algorithm did something that no previous search engine could. It measured not just how often a page talked about a topic, but how respected it was within the global network of knowledge. It captured not only popularity, but authority. If a highly respected page linked to you, your importance increased. If many important pages linked to you, your importance skyrocketed. And importantly, if you linked out to many pages, your vote was essentially split among them, which prevented any single page from artificially boosting others. This was not merely an engineering solution, it was a philosophical one. It treated the web like a living, citation-based ecosystem, more like a digital academic library than a keyword billboard. The original PageRank paper illustrates this concept using small, easy-to-visualize example networks, simple graphs of nodes and links that demonstrate how iterative computation gradually distributes importance through the network. These examples show how even pages with no direct inbound links can still accumulate importance indirectly if they are reached through chains of important pages. They show how loops behave, how weight naturally propagates, and how the algorithm gracefully handles complex topologies. The paper also dives into how to handle dangling links, how to compute PageRank efficiently using power iteration, and how the algorithm remains stable even for massively large graphs. These details might sound technical, but they form the backbone of Google's early success. Before PageRank, search engines were cluttered with irrelevant results. After PageRank, search became useful, reliable, and truly reflective of the web's collective judgment. The impact was immediate. The algorithm's ability to identify authoritative sources allowed Google to leapfrog competitors because instead of simply matching keywords, Google was ranking based on the structure of the entire web. Imagine walking into that infinite library again, except now, the books arrange themselves dynamically, placing the best ones closest to the entrance, based on what the entire network of knowledge believes matters most. PageRank wasn't just a ranking algorithm. It was the foundation that transformed the web into something navigable, something meaningful, something you could actually use. But this video isn't just about the math or the history. It's about the story, the idea that a single conceptual shift, seeing links as votes instead of mere connections, could alter the course of the digital age. And there's another powerful point from the paper that often gets overlooked. PageRank is robust. The authors show that even if some parts of the web are messy or unreliable, the algorithm still converges to meaningful values. It doesn't fall apart with noise. It doesn't crumble with partial data. It smooths out irregularities as it computes the importance vector. That robustness was essential in the early web, which was far more chaotic than today. Billions of pages, many with errors, loops, broken links, or strange structures, yet PageRank still worked. Another subtle but important insight from the paper is that PageRank naturally rewards quality over quantity. A spam page can generate thousands of outbound links, but that doesn't increase its importance. And getting links from unimportant pages barely moves your score. You need credible endorsements. That's what made PageRank so resistant to manipulation, for a while at least. It also created a feedback loop that shaped the web's evolution. Websites began caring about earning high-quality links. Content creators focused on being cited by authoritative pages. Entire industries emerged around SEO, largely because of PageRank's influence. Now imagine being Larry Page and Sergey Brin, sitting in a Stanford dorm room, watching your iterative algorithm propagate through a snapshot of the web. You're watching scores stabilize, seeing which pages rise to the top, not because you told the algorithm what was important, but because the web itself decided. That's the magic of PageRank. It didn't impose structure on the web, it revealed the structure that was already there. Of course, the algorithm wasn't perfect. It didn't consider text content deeply. It didn't understand meaning. It didn't fight spam forever. But as a foundational idea, it changed everything. And the paper ends by highlighting how PageRank could power a new generation of search engines, engines capable of scaling to the immense size of the web while still producing relevant results. That prediction wasn't just correct, it reshaped the trajectory of the internet. And today, even though Google's ranking algorithms have grown vastly more complex, PageRank remains one of the most iconic and influential ideas in computer science. It's a reminder that sometimes, the simplest models, like imagining a random surfer clicking around, can unlock insights that move the world forward. It's a reminder that structure matters, that networks reveal hidden truths, and that elegant mathematics can quietly power revolutions. So the next time you search for something online and instantly get meaningful results, remember that behind that effortless experience is a brilliant piece of mathematics born out of curiosity, creativity, and the desire to bring order to chaos. Thank you so much for watching this deep dive into the origins and inner workings of one of the most important algorithms ever created. If you enjoyed this story, if you love videos that reveal the hidden engines driving the digital world, make sure you like this video, subscribe to the channel, and leave a comment telling us what groundbreaking paper or algorithm you want us to explore next. Your engagement helps us keep creating videos just like this. And with that, I'll see you in the next one.